Good morning, scholars. Today we are going to be working on our new three-dimensional unit. We're in our last unit, Unit 10, as we come up to the end of the school year, and we're going to start to work with objects which have like full volume, full mass, or three-dimensional objects like cubes and squares and things like that. Um, oh, yeah, thanks. Yeah, see you later. So what we're going to be talking about today is kind of just the introductory verbiage associated with this, kind of like which letters we're going to use, what the nomenclature, if you will, associated with all of these objects. What I'd like for you to do is make sure to go into Google Classroom today. There is a text file up there, which is a list of all of the definitions and things like that. We're going to use that kind of to set our lesson together for today.
Let's get started on this first vocabulary sheet that's up on our Google Classroom for today. Just as our previous unit, we're going to start off with some vocabulary or verbiage or nomenclature around these solid objects, these figures, these polyhedrons and such. What we're first going to look at here, example on the right hand side, I'm going to point to how these different definitions relate to our figure that's onto the right. Our first one's going to be polyhedron. It's a multi-sided object. It's a solid essentially, where all the surfaces are polygons, basically like a three-dimensional closed space. A big word that we're going to rely a lot upon is going to be this term face. And the basic notion behind a face is that it's going to be one of these three-dimensional sides of a figure. More importantly, this is going to be with these flat polyhedron-like figures where we can actually go ahead and point to a particular, like say, side of the figure, like the top or the back side, the bottom side, the base, if you will. Our next term is going to be the edge. The edge, pretty simple. It's just where two of our faces meet, or what you can call as two of our planes of our object make a contact. In this particular figure here, one of our edges is going to be this top line here, where basically those two pieces of paper, those two pieces of the box enclose on one another. The next is going to be the vertex. We talked about a vertex being like the angle point. In a vertex, we're just going to take that in a three-dimensional way and say it's where at least three different planes or three different line segments come and make contact with one another. The last term here we're going to look at is going to be base. The base, similar like in a trapezoid where we refer to typically the base as the two parallel portions, the base in a solid is going to be the one that's perpendicular to the height, where it forms that 90-degree angle. In this particular example here, our height is going to be the one that presumably is going to go up and down. Our base is going to be the bottom of the box where those objects come up out of it. Next up, let's look towards the center of the page. And in the center, we're going to find essentially how we begin to describe specific types of three-dimensional figures. The first one we're looking at here are prisms. In terms of being a polyhedron, they're a closed figure. They're not like an object with a missing top or something like that, but they're closed figures. In this particular example here, the big takeaway from a prism is that it's going to have at least two congruent bases. So for instance, our box here, we have a top and a bottom to it. Those two pieces, which are perpendicular to the height, are going to be congruent. It's like we're taking a set of books and just stacking them all on top of each other. The bottom page of the book is congruent to the top page, the back cover and the cover. Next up, what we can also say is that all of our lateral faces are parallelograms. And what we mean by lateral faces, it's going to be the portions that make its way around to eventually connect our bases. They're all going to be parallelograms, or they're what we can say is their opposite sides, like in a two-dimensional parallelogram, are going to be congruent with one another, those paired pieces, but they're also going to be parallel in a way where their angles are always the same. If we look at this particular figure here, We can see how our top and our bottom are parallel with one another. These bases are parallel. Our sides to the boxes, that whole side, the bottom line and the top line, are parallel with one another. They're parallelograms. The left and right side are all parallel as well. If we look at this hexagonal prism over here, we can see how this section we can fill in one of these lateral planes. The top and bottom of it are parallel with one another, as well as the left and the right side. When we get to objects like pyramids, we start to have different terminology, but more so we lack this notion of essentially like parallelism with all of the particular faces. The big takeaway from the pyramids is that we're just like in Egypt or throughout Central Americas, our pyramid structures are going to have what we would describe as some type of flat shaped surface. And here we can see an example of a hexagonal pyramid. Along the bottom here, we have one with like what perceives to be like a square or rectangular bottom, but the lines come up and eventually fixate on one singular point, what we call a singular vertex at its apex. If we take up all the little portions from the bottom base and eventually connect them up to one another, they all meet at one single spot. Versus our prisms where we have those two shapes duplicating on the top and the bottom. Lastly, all the lateral faces on these triangular pyramids are not necessarily going to be congruent. You can kind of wiggle and wobble the figure to produce different side lengths and things like that. Like for instance here, instead of having the vertex perpendicular to the height, it's been kind of pulled over. So the side that's been pulled over has a shorter distance to carry up towards versus this piece that has to stretch all the way across the length and the height of the object. Our last terms that we're going to work with here are one of the at least in terms of cylinders, it's going to be the more common of the many three-dimensional objects. With a cylinder, we're talking about now a curved type of figure. Here we have circular bases, which are parallel to one another. And from there, we have curved surfaces that go around, just like a soda can, if you will, or an Arizona can. Cones is going to be kind of a combination of pyramids and cylinders. With a cone, like an ice cream cone, we're going to have that singular vertex at the top or bottom, stretching out to that flat plane along the top, which happens to be in cones, circular. And then we have the circular body descending in terms of physical size. What we're going to do now is go to our next page of vocabulary. We should see in that same Google Classroom document file is a set of definitions that we're going to use for our figures that are present here. When we begin to work with three-dimensional objects, we're now no longer dealing with in terms of things like area or circumference. We're taking consider height. We're actually adding more mass to our objects. The way that we denote these are with terminology like a solid and volume. A solid is something that we consider to be three-dimensional. By three-dimensional, we mean something with width, height, and depth. There's actual like mass and tangibility to it. Just like you can have a credit card or you can have like a wallet with actual physical thickness associated with it. When we go to calculate how much space, how much physical mass these objects take up in the real world, we're going to use the term volume. When we measure with volume, similar to area when we said, oh, inches squared, because we counted for a width and a length, within solids, we're considering 3 dimensions. So when we use our notation, we're going to have our units cubed. We don't usually say to the third, we say cubed, C-U-B-E-D. So volume is going to be how much size it takes up. Equations are going to be a little bit more variable with three-dimensional objects because of the lack of proportionality that exists. Like for instance, in a cone, you have to account for the bottom that is there, which might be really, really, really tiny, versus the amount of space that the top of the cone can take up, where the actual, ice cream ball goes. Types of various solids that we've already seen so far. We have prisms, pyramids, cylinders, cones, spheres, cubes, and things along those lines. We won't get too much in terms of really advanced say like 20-sided or tetrahedron figures, but we're going to have some type of language that's going to allow us to still calculate those or still kind of comprehend them. The next thing I would like to do is talk about one of the ways that we go ahead and name some of these figures. One thing that we can say about all solids, we include the right when a center of a second base or apex point is right above its first base. When we have specific names for these figures, what this definition is trying to say, when we have nice convenient naming, oftentimes we're going to see the center of the second base, like for instance this cone, is going to be right above or perpendicular to the base, so it's central. Versus in our previous page, this pyramid that we have here, we do know that it's a pyramid, loosely speaking, but if we had to go ahead and define it, and you can then go to, say, a 3D printer and just hit a button and say, oh, I need a pyramid that's 4 inches tall, you don't have necessarily that ability, because we then have to go ahead and consider kind of that slant that exists. So a lot of the solid names are going to be these very rigid structures, where specifically our vertex is going to be perpendicular, or what we would call our second base. The top portion is going to be centralized. Okay, so there's a couple different ways that we go about describing the transformation of two-dimensional figures into a three-dimensional figure. Some of the ways that we can go ahead and do this is with what we would say is stacking versus rotating. Rotating as a particular type of concept, we can go ahead and say if we take our democracy prep card, rotation, kind of as the name implies, allows us to take a two-dimensional object, say like a rectangle or a revolving door, and when we rotate it on an axis, on a centralized point, we end up creating a three-dimensional figure. When we're talking about something like, say, a two-dimensional object like a rotating door, we can say that the figure which itself is being rotated is a rectangle. But when it actually gets rotated around everything, we end up having what we would call specifically a right cylinder. And there's multiple ways that we can go ahead and generate a right cylinder. Like if we look at this stack of DVDs that's here, we end up being able to take a flat circular object, say like as a quarter, and if we stack a whole bunch of quarters on top of each other, we get this nice long chamber, which we'll describe in a similar fashion as a right cylinder. And we shaped it, we came about with kind of the same exact figure by using still a circle. So depending upon how you're rotating or how you're stacking something is going to allow you to take a two-dimensional object and turn it into 3 dimensions. Let's look at this question towards the bottom. It says, if you stack a bunch of pizza slices on top of one another, and we think about a pizza slice being triangular, what type of figure would we end up creating? Well, we can think about the original shape of a slice of pizza being somewhat triangular, or having a little curve at the end for our round crust. If we end up stacking these figures right on top of one another, we end up creating what's called a right triangular prism. And the reason why we're saying right triangular is we're adding that specificity from before, where our figure, similar up to the top here, is going to be a solid where the center or the second base is going to be directly above the bottom piece. If we take a whole bunch of pieces, slices of pizza, we end up creating that theoretical like cake shape. And if you have nice artistic ability, you can go ahead and laugh at me here if you'd like. We end up getting a nice triangular feature. If you're way into drawing three-dimensional objects is when your patience starts to get pushed. There's a lot of great YouTube channels that show you kind of how to go ahead and draw a lot of that stuff using like geometric terms. What we're going to do now is switch to a video website called GeoGebra. And it's a great website that allows us to interact with various types of three-dimensional and two-dimensional models. And it's a good way to kind of just like see and play around with figures and get a better understanding of them. Here we're going to have a few examples of taking two-dimensional objects along the bottom here and rotating them around a specific line. Here in this example, we can say that this black dotted line, oftentimes you'll see it as line M or line R. We're going to use motion or movement around this particular line to create these three-dimensional figures on the top here. In this blue and red figure, we have a sphere. We have circular around the sides. We have a flat top and bottom, what we would properly call a cylinder, S-Y-L-I-N-D-E-R, just like in our previous example. In the next figure, our orange and purple, we have a triangle rotating around. And if we look along the top of our triangle here, it's our tiny point, which is going to be generated along the top of this cone here. Nice large circular base coming up to a finite individual point on the top. Next, in this blue and green example, we have basically what looks like the beginning of a trapezoid. We have a parallel top and a parallel bottom. Moving this object around that point, or sorry, that line of M, we can end up calling this figure what's commonly called like a lampshade. In our last one, we have a portion of a circle, and when it's rotated around our line M, we end up getting a sphere. So for these objects, we're just beginning to learn the names. Throughout our unit, we're going to get a better understanding of exactly kind of the nomenclature around them and how we generate these names. What I'd like for you to do is, within Google Classroom, I want you to open up your independent practice. It's a rather short one today. I'm going to give you some examples on specifically what's the logic behind, or like how to go ahead and name some of these figures. And then throughout next week, we're going to learn how to basically divide up portions of three-dimensional figures and then eventually draw some type of calculations associated with them. As always, if you have questions, please feel free to come into our office hours, and I'll be more than happy to help provide you with some assistance. But until next time, have a nice day.